Good morning, everybody. As I promised in my little brief welcome message, we have our first session of the day led by Michael. He will be speaking on a step-by-step guide to designing heating and cooling surface systems. Again, if anybody has any questions, feel free to put them in the chat function here on the right-hand side of the page. Michael has asked if we have like a time period right at the end of the session where we'll be asking all of our questions. So do not fret. I will be making sure that each and every question gets a chance. All right. Thank you very much. And Michael, you're good to go.
Thank you. So my name is Michal Strzeszewski, and I'm going to show you how to design the heating and cooling surface systems using our software Audytor SET. We're the software company Sankom, based in Warsaw, Poland. And I will start with the short presentation of slides, and then I will show you the live program. So a few words about the core of the software development team. Let me introduce Piotr Wereszczyński, the main author of the program, then myself. Piotr is the former employee of Warsaw University of Technology, but now he doesn't work at university anymore. He has started the company Sankom. I still part-time work at the university. And the third person I would like to mention is Piotr Narowski. He's also an employee of Warsaw University of Technology. Altogether, the team is about 20 people, and mostly engineers with software experience. We've been developing the software for more than 25 years now, and our software is available in many languages like English, German, Spanish, or Chinese, for example. And let me introduce the main applications that we have developed. The first application is Audytor HL. HL, it's the program to create the 3D models of the buildings and calculate the heat load of the rooms and the building. And then we have the modules, the program that we started developing separately, but now we have joined them together. CH, it's a model for the central heating systems. CC, the model for the central cooling systems with ice-water network. And H2O, this is the module to design the internal water supply systems. Now we have integrated all three modules in one program that we called Audytor SET. This is set of these three models. And a part of our main general version, we have more than 30 corporate versions that are sponsored by some manufacturers, and then you can get such a version of the software for a reduced price, or in many cases even free of charge. And we have a very huge database. So inside the program, you have technical information about a lot of devices. For example, more than 58,000 of radiators, 16,000 different accessories tabs, and more than 1,400 pipe types. And here a few examples of the buildings, because we pay attention that the software works also efficiently with the big designs. So here you've got the very big underground railway station in central Poland, in Łódź. And this is the model of the station in our program, and this is the picture of the real building. So most of the parts of this underground, because it's not underground in the meaning of the underground in the city, it's just this main railway system, but the station just underground, and you can see only a little bit over it. And this is the huge residential complex. So we test our software with the real designs, and sometimes with the designs like this. So this is not a real design. This was just made quickly by copying. But in this example, we have 8,700 radiators, and we use this to test to make the program more efficient. You can use it for big designs. And this is the building of the Nicholas Copernicus University in Toruń, the heating system of this building, in fact. And this is a big residential building. Before we go to the live program, let me explain you some main principles of working with the software. So again, Audytor SET, this is the program that I'm going to present today, consists of 3 modules, CH for central heating, CC for central cooling, and H2O for water supply system. So we will be working mainly with CH module for heating, because the program can design the surface systems for the heating mode, but then we can also calculate the resulting cooling power when switching to a cooling module, so supplying with the low temperature water. And we recently added also the 4th module, FC. FC stands for fast calc. This is for fast estimation of heat load, as well as for preliminary calculations of the not completely ready designs. And now I will show you the idea with very small design, because probably it's better to explain the idea. So in one model, in one project, we can design different types of systems, so heating systems, cooling systems with ice-water network, and domestic water supply systems. And when we design the systems, it's probably better to see just one system at a time, but at a certain moment, it's good to switch on all the systems, and in that way, we can find the possible collisions between the systems. And very important nowadays function is that after designing the systems, we can export the model of the system to Revit for the BIM technology, to make it available also for other participants in the investment process. Here you can see the example of the water supply system. As in the left-hand side, you can see the model in our software, and on the right-hand side, already the model of the same system in Revit proper. And generally, there are 2 methods of designing the systems. A more traditional method, designing on diagram. So in this method, you just create the diagram of the system, then program performs the calculations, selects the sizes of radiators, diameters of pipes, etc. And the second, more modern, more advanced method is designing on the plan views. And this method is much more efficient, I think. The general idea of this method is that we draw the system on the plan view, on the flat plan view, because it's much faster and easier than in 3D, but the program creates the 3D model automatically. The 3rd dimension is created automatically by the program. So that was the introduction. Now let me show you the program. I purposely changed the resolution of my screen that you can see the letters bigger, because you may use different devices to watch this training. However, of course, for the big designs, it's much more efficient to work with pretty big screen and high resolution. However, the hardware requirements of the programs are very, very moderate, and even if you have pretty slow laptop with small screen, you can still work with this software. However, as I said, for big designs, it will be more efficient to have pretty big screen and not the slowest machine. Okay, so this is the example of the small system that I have already designed, and I will show you in a moment how to do it. On the left-hand side, you can see the axonometrical drawing. On the right-hand side, the 3D visualization of the system, and you can also see the plan views. So let me start with the new project. It's a good idea to save it to disk, to create the file with data. And then, as the first step, we will import the plans of the building. The most efficient way is to import already the results from HL program, the model. And here we've got the example of such model. And we have the plan views of the buildings, so the basement, the ground floor, and some attic. And in this case, as we obtain the plan views from HL program, we obtain the plan views, but also the heat loads. If we go to data menu, rooms, and then as you see in the HL column, you can see the heat loads of the room. They are in green color. It means they were imported from HL program. But if you prefer other values, you can override it. For example, let's say that we want heat the basement, so we can override it with zeros. And as you see, the zeros that I have entered now are in black font. Black color means that they were entered here manually, and in that way I have overwritten the imported values. And now let's go to global data. You've got some basic description of the buildings. All green fields are not obligatory. Then in here we can activate the models. So for the beginning, we will use the CH model, so it should be active. But for the time being, I will deactivate the CC and H2 model. Generally, if we don't use, at least at the beginning, the specific model, it's better to deactivate it, so the program will require less amount of data. So for the beginning, only CH model is active. Then I have to select a few information. So pipes, I have to select pipe and associate that with the letters. In this field, we are selecting the main pipes, the pipes that will be used to construct the main pipes. So we have a lot of types, more than 150. We can select the manufacturer, for example, can company, and we have to select something. For example, this pipe. And we have associated it to letter A. As we see, we have more letters. If necessary, we can use different types of pipes in one design. And we also should select the default insulation. And at this point, this red stripe here has disappeared, so all the obligatory data were already entered. However, if we design the surface systems, we have to select a few more. So as you see here, you have the section in global data, the section surface systems. So we have to start with this section before we go to drawings. Let's start with the first tab in the section basic data. And first, we select which types of surface we're going to design. We have the floor, ceiling, and walls. Let's say that for the moment we will use only the floor systems, and depending on the what we select here, the next tabs will be active or not active. In this example, at the moment, only floor systems is active, ceiling and wall is not available. So, and in this basic data, we can select the default values, default parameters for the designing, for calculations, like the minimum temperature drop, maximum temperature drop, maximum pressure drops, minimum velocity, etc. These values are default for all types of surfaces, but if necessary, we can redefine it and create other values separately for floors, walls, and ceiling. Then we can go to the floor system, and here we can select the default data just for the heating and cooling floors. Again, all these values will be default. It means that we can modify it later on if necessary. First, here we have to select the pipe system for underfloor heating system. So, for example, Kamtaker. Then we can select the pipe. And here we select the pipe, not the main pipes, but the pipes for the heating and cooling coils. Let's try the first one. And as you see, it's got the diameters between the 14 and 20. And here we have the default available combinations of diameters and spacing. As you see, by default, the spacing 5 centimeters, it's not available. It means the program won't select it. By default, the program starts with 10 centimeters, goes up to 30. But if necessary, we can modify it. And also here, we can define the default diameter that will be used. If we don't change it, by default, it's 16. And then we should select the structure of the heating floor, default one, let's say the standard one. We can then create exceptions. And floor covering, probably we would need something. Let me select maybe ceramic tiles. And then you have here the standard layers. If you have more unique, untypical solution, then later on you can modify. But at this step, we just go with the standard layers of underfloor heating system, so the floor coverings, grid, system board, etc. As you see, you have already some suggestion in green font, and if you prefer, you can change it. What is not suggested, it's a ceiling or floor, how you call it. Let's say in our example, it will be internal ceiling with the specific U value, for example, 1.5. And here again, you have the parameters for calculation, minimum temperature drop, maximum temperature drop, etc. And these values are inherited from the global values for all the systems. If you prefer the values for the floor systems, you can change it here. If you don't need to change it, you just leave it. And also you can select the calculation method. We have calculation method according to EN 1264 or the trapezoid method, analytical method. This is for calculation the power, the heat power of the heating system. Okay, so Now we are ready with the global data. So let me summarize it. We have basic data, and here we have the default data for all the surface systems, and then we can create them separately for floor, ceiling, and wall. Maybe let's start with floor systems only. And now we can create different construction types because we can have more than one solution in our design. So to do it, we select data and constructions of surface radiators. When we open the catalog, this is the catalog of the construction. And at this point already we have one construction default for floor. So that was created automatically, and as you see, everything is in green. It means that this is exact copy. Maybe copy is not the right word because it's not a copy, it's just inherited from the global data, but now we can create a modification. So this standard solution, it's a ceramic tiles. So let me create now the version with the marble covering. So I will add a new construction tab. I will do it here with add button. The program asks me what type of surface I wish to create. Okay, underfloor radiator. And again, everything is in green. So unless I change something, unless I set something here, the program inherits all values from the global data. So let me change the floor covering into marble. And also I will write the symbol marble. And as you see, I have created another version. All the parameters of the constructions are the same except for the floor covering. As you see, floor covering here it's in black font. It means that I have set this value here manually, and it's set here rather than inherited from global data. Okay, I have already two construction types, so I can go to drawings now. And let me go to drawings and maybe let's start here. And generally, to draw the surface system, the floor system, I will use this tab. This is the tab with the tools dedicated for underfloor heating systems. And I will place the heating zone. First, I will show how to do it manually. So this is this button. This is the pull down button. This black triangle means that it's pull down button. When I press and hold for a moment the left mouse key, such a small list opens, and then I can select, okay, in the living room, I will prefer model. And now I will draw a polygon that will create the heating coil. Now I can use the right mouse key, and that will enable me drawing another coil. And both of them are on the marble. Now I would like to show you how you can create such a zone automatically. I can do it if I select the room zones. So I will go to the room zones mode. Now I will use Ctrl-A. That in this case I selected all the elements. Like in other software, Ctrl-A selects all the elements, but now I'm in the room zone mode. It means that all the elements will be only the room zones. I will unselect the living room because I don't want any more radiators here. And then I can press this button with this lightning. It means very fast creation. And then indeed I will use the default construction rather than marble. And in this way I have created other heating zones. So this works very efficiently if I have the plan views from Audytor HL software. But if you prefer not to use the software, only Audytor SET, so you can import also the AutoCAD DWG drawings. The only thing that you have to do it, you have to over that AutoCAD drawing draw the room zones, so the program knows where the rooms are. Okay, so we have the room zone. So now we have to create the manifold and connect them. So let's go to the accessories tab and apartment manifold. And I have already selected before our session an example. What is important is that we use the manifold that is dedicated for the floor system, that's got appropriate valves, rather than simple manifolds that is only for the convective heating system. Okay, so now I will connect the manifolds with the heating zones. I will make it much bigger that you can watch it well. You can see it well even with this pretty low resolution. I will draw the pair of the pipes, supply and return, because it's faster. So then one click here, one click here, one click here, and okay, I have connected the first heating zone. So then I will go to the next one. Oh, here I have clicked in a slightly wrong way. I should click at the border, but I can move these points. So when you see the exclamation mark, it means that the pipe is not connected to anything. And now it's connected correctly. So still 2. I can purposely go with not the shortest way, because I would like to use these pipes, these connection pipes, also as a heating pipes. Okay, now I have committed a small mistake because I haven't connected this one. But let me say, maybe it's not a very typical solution, but as an exception, the program allows that we can connect it with the T-joints. Probably most times you won't do it, but as an exception, the program will, I believe, it should accept it. Also such solution. And we also need to, maybe it's not obligatory, but the drawing will look better if I make this manifold shorter. And now I will create a riser. To create a riser, we'll use this button here, the riser as seen on the plan view. We can create separately the supply and return risers or the pair already. Let's say that risers will be in the wall. And then I will connect the manifolds with the riser. I haven't changed the standard level of the pipes, which is -5 centimeters, 5 centimeters under the floor surface. Maybe here to go under this heating zone, I should go deeper. But there is an exception, because if I connect in a moment the pipes to manifolds, so the first segment of the such pipe is on the level of the manifold. So then pretty quickly I have to click one more to create automatically the vertical pipe and to go on the floor. So let's select the pair. So one click here at the side of manifold. Then here pretty fast, meaning pretty close, additional click. So here the small vertical pipes will be created. And then here, let's say it's on another level. And as you see, where was this, let's say, additional click, the second click, we can see these circles. It means the program has created vertical pipes. We can see them in the 3D visualization. So first we've got the pipes that are on the level of manifolds, and then we go under the floor, because here we've got the door, so we cannot go on the level of manifold. Okay, so we have the riser only, but it's only on this floor. So then I will copy it downwards to the basement, and then here I should draw the pipes, the basement, and the heat source. We have the different heat sources like boilers, etc. However, we don't have yet the library, so you don't have the real products, the heat pumps, boilers, etc. You just have to enter a few values. I will show in a moment. I will use this very abstract heat source. It can be, for example, a heat pump. And here I have to enter the values. Very important is the supply temperature. Here we've got which is far too high for the surface system. We will have to enter here the lower value, but let's say that we have forgotten about that. I will show you, because I want to show you the diagnostics. Then the temperature drop will be probably different. And also there are two columns with no default values, the pressure drop and the water capacity of the heat source. The program doesn't suggest anything because it can be different, but it means that we have to enter. If we don't enter it, the calculations wouldn't be possible. So let me show you how the diagnostics work. I started the calculations and I obtained this message that it wasn't possible because there is some problem with data. Okay, let's see the lists of messages. And there are different types of messages. White is just information. Yellow, it's a warning. Pink, it's pretty serious warning. And red, it's serious problem. And here you've got the two serious problems, that the value, this field cannot be empty. And we can double click the message and the program moves us to appropriate place. And we have three possibilities. We can enter the pressure drop. We can enter the zeta values of kV, let's say zeta 4, for example, in a simplified way, and let's say 15 liters. So I have corrected these two errors. I can press also F9 to start the calculations. And now there wasn't any problem with data as such. The calculations were performed, but after performing the calculations, the program checks also the results. And when we see, so as you see before, there were only 2 messages. Now we have almost 40, but these are different times, because before you saw the critical problems with data. Now this is the problem with the results. So let's say that we'll switch the yellow and pink and white off. So we see only the red ones. Some of them results from the fact that we have also next story. We haven't designed the system yet. So if that was the final design, of course, that would be the serious mistake. In our case, it's not. But what you can see here, that you have a very high floor surface temperature, 36, when 29 is permissible. Also, the power density exceeds this limit value. These two messages, in fact, this is the same problem, just presenting that from the different perspective. The reason is very simple. As I told you, this temperature, it's much too high. So to correct this problem, we have to go to the heat source and change 45, which is more typical, and temperature drop 10. I can repeat the calculations and see the diagnostics. And as you see, this temperature problem has disappeared. Only 4 rooms with lacking the system. So let's go to the next floor. I will copy now the riser to the next floor, and probably in the same way I will add the heating zones. And then the manifold. The same way. And then with little experience, a little maybe better to say, you can do it pretty fast. Oh, here something was not correctly connected. If something goes wrong, you can edit, of course, all these segments. However, in some cases, it may be faster to delete it and start it from the beginning. Oh, here also I have clicked not exactly in the right position, so this one I can correct by editing. So all the heating zones are connected. Now I will reduce the length of the manifold. And again, I have to connect manifold to, so just one click is enough. Here, I think I will move these pipes, so I can move, select 2 pipes to move 2 pipes at the same time, and it's good to hold F2 key, so all the connections are maintained. And I will try again, connection manifolds. The products connected up to the room. Okay, so and here. Sometimes when something is not correctly connected, sorry, this sometimes it's just enough to click it. This is, I think, not necessary. We have to connect it to the side. Yeah, Oh, it's okay. But the vertical pipe is missing here, so I can use this tool to add a new point. Okay, and let me start the calculation. The calculations will also test whether everything is connected. Oh, indeed, the calculations were possible. And as you see, all serious problems have disappeared. There are some pink ones. I should add also the pump. Also, the velocity is pretty low, so I will try change the default diameter. And let's check now. Yeah, depending here, yeah, the velocity is pretty low because of the flow, so we can also change the default temperature drop, like for example 5 to 7. So as you see, you can play with that and see how different parameters influence the results. So as you see, yeah, now in most coils we have the velocity pretty close. What is important is that we have two types of drawings. So far, I have been showing you only the drawings with the data, but after performing calculations, you can also see the drawings with the results. To see them, you have a few possibilities. You can go to results and then drawings. If you don't remember any shortcuts, you can always easily access it from menu. But there's also the speed button here, or you can just press Control Tab. Control Tab changes between the drawings with data and drawings with the results. So here, as you see, you've got selected, for example, you have the area, the heat power, but very important also the pipe diameter and spacing. Here you can see a little problem that the label of the room overlaps the label of the underfloor heating coil. So to change it, we have to go back to drawings with data. Now we can access and move the labels appropriately. Now we have to repeat the calculation because the drawings of the results are updated during the calculation. And when we switch into the drawings of the results, now you see the labels were updated. You can edit because there is a lot of different values available. So you can select which ones are important for you. If you double click the label, so editor opens, and then if you have for the room, we have here info temperature, but we can, for example, add also the heat load. We can also create the shape, the frames, maybe this one. And as you see now, we can see also the heat load of the room. So the labels of the rooms and the heating coils are added automatically. We only sometimes, as in this example, we have to shift them so they don't overlap. But if we wish to present the diameter or the information about the main pipes, we have to add the label manually. For example, here. And here it says that the diameter is cal. It means that we don't enforce, the program should calculate and select the diameter. And now after repeating the calculation, if we go to the drawings with the results, you can see the selected diameter of this pipe. And the last function we would like to show you before we go to question session. So it's the possibility of calculating the resulting cooling power. So let's go to global data again. And we have to add this option to heating source because we treat the heating as main function and the cooling as so-called second function. So we can have to add it here. However, the field for that won't be available unless we activate the cooling module. So first we have to click Basic Data tab and activate the CC module. Now, if we open the Heat Source tab, a new field has appeared, Calculate Cooling. So we activate it. But then we can also specify the default temperature, supply temperature during the cooling mode. And as we go back to the data about the room, the program for the assumed temperature in summer and the humidity, the program calculates the dew point and then adds also the 2 degrees Celsius kind of safety margin. So tries to get the temperature on the floor surface 2 points more, so 19.6 at least, to avoid the water vapor condensation. So now when we repeat the calculation with this option on, and when we open the tables with the results, and then the surface heating surface radiators. So as you see, these tables have got lots of the columns because the program just possesses lots of information, but you can switch off some of them. You can select, right-click and select Format Table, and you can decide which columns should be visible. But the important thing now is that we have also this blue section. These are the calculation for resulting cooling power. So we assume that the flows are calculated for the heating mode and are maintained also during the cooling period. And here in this tab, you can check the resulting cooling power. You have also other information, for example, the minimum surface temperature to avoid this water vapor condensation. As you see, it's 2 degrees higher than what was calculated to have this 2 degrees safety, and then you can see the resulted surface temperature, the extreme values and the mean values. As you see, they are over this minimum level. So this was my presentation. If you would like to test the software, you can go to our website sankom.net and you can download the free trial version that will work, I think, for 1 month. So you can test the software for free for 1 month, and you can use it even for the commercial purposes within this period. So now I am ready for the questions.
Wonderful. Thank you very much. That was fantastic. So far we have 1 question. So I do ask anybody that's sitting in on a session today to make sure that this is your time to ask some questions. So please type it in the chat. So the one question we have is from Clement. It was shown that Sankom highlights entrances between, I think that's the word, I don't know what word you're trying to say there, but between various plumbing and mechanical equipment. Are possible structural intersections only dealt with in Revit or other other similar CAD?
Could you read the question a bit slower, please, so I can?
Yeah, that's no problem. I am notorious for speaking very quickly. So the question was, it was shown that Sankom highlights entrances between various plumbing and mechanical equipment. Are there possible structural intersections only dealt with in Revit or other similar CAD?
Okay, for the time being, the software cooperates only with Revit, I mean directly, so it can export the, let me show, we have here a possibility of exporting data or results into Revit to have the really 3D model. It doesn't cooperate doesn't have this function of other similar software. Directly, you can just export this general file, as you see, DWG, DXF, that can be useful to some degree, but there are graphical files. In comparison, in case of Revit, you've got 3D files and you have the logical model. So depending which function you use, exporting data gives you the possibility to export it even if the model is not ready and we cannot, for this reason, perform calculations. But you can already export it at this stage. With export of results, it exports a part of the graphical 3D model, also the properties of all the elements, and also the result of calculations like heating power, water velocity, selected diameter, and so on and so on. But unfortunately, for the time being, we export that directly to Revit. The reason for that is that the Autodesk just was ready to cooperate with us, supplied us with all the necessary information. However, we are working on export also to IFC format, that with this general format, and in the closest future, I hope it will be also possible to export it also to other similar software.
Thank you.
I don't know if that answers the questions fully.
Okay, so we'll jump to the next question. So Luciano asks, is there an option in the software settings to change from the metric system to imperial?
At this moment, there's only metric system. We are working also on imperial system, and this would be a question for me if it's important for your market.
Okay.
If somebody could write a message in the meantime.
Okay, we have another question. So Rex asks, what would be a good delta T for radiant heating and for radiant cooling?
For radiant heating, normally it's pretty low. It's between 5 and 15 degrees Celsius. And generally, lower delta T means the higher flow and also a bit higher power. Mm-hmm. So generally, we work with pretty low temperature drop for the surface system, much lower than in case of convective heating system. Sometimes we can have it in some cases a bit higher, up to 15 degrees Celsius, in case when we have a pretty low heat load and we have excess of power. Generally, if you design the only cooling systems, then as far as I know, this temperature drop can be even a little bit lower. In case of cooling, the other temperature difference means the rise of temperature. However, in our software at the moment, like that, that we present the flow for the heating system, and as you see, for cooling mode, you enter only the supply temperature. You don't enter the temperature difference, because the temperature difference results from the flow. But let me have a look. As you see, in this example, these are the calculated values. So as you see, we can sort it. This can be useful function. So in this example, you've got starting from almost 3 to 8.
Greg did have a follow-up. He asked in question 15, I'm assuming that meant in relation to the delta T for radiant heating. Can you expand on a little bit of why you gave the numbers between 5 and 15?
5 and 15? Yes. These are the standard values suggested by the program, as you see. So to answer the question a little bit wider, so these are the default values. The minimum is 5, maximum is 15. If you believe that in your design another value would be more reasonable, of course you can change it. However, the reasons for why not to go much lower than 5? In case of a very low temperature drop, to obtain the very low temperature drop, you would need a very high flow. And high flow first will result with very high pressure drop. And that would mean very high electricity costs of pumping. Also, we can have the risk of the noises. So generally, we reduce the temperature drop if we need to increase the power, but generally it's not recommended to go under 5. But if you prefer, let me see, the program accepts even from 1. But I think 1 is rather low. On the other hand, 15, it's already pretty high. And if you have higher temperature drop than 15 degrees Celsius or Kelvins, in case of temperature difference is the same, then it would mean the opposite. The flow would be very low. So, okay, low temperature drop, low energy costs. However, such very low flows could be very hard to control. So the system won't be that stable.
Well, thank you very much. Does anybody else have any questions? We have 1:40 left in today's broadcast. Forever hold your peace. Okay, so I'm going to I'll do a little wrap up. So thank you again for this wonderful session. For everybody still joining in today, we still have some people. Dave Holdolf's next session will be beginning in just under 2 minutes. He will be focusing on proper sizing and installation for domestic hot water recirculation. So make sure you attend that. And thank you very much and enjoy everybody. Seeing you guys in the next sessions.
Thank you very much for your attention. It was a pleasure.